Hi, I'm Derrel Martin. I'm a professor in the Biological Systems Engineering Department. I work in irrigation and water resource engineering. And today I want to visit with you about managing sprinkler irrigation systems, primarily center pivots, to best utilize the water resource and to protect water quality. We know that most of the land irrigated in the state of Nebraska today is irrigated with center pivots. In fact, more than half the land in the United States is irrigated with center pivots. In Nebraska today, we're about 85% of the land. And so they have a great ability to manage if you can operate the pivot correctly. So we're going to look at some of the things we ought to think about to manage that pivot. So here's a list of some of the things we're going to talk about a little bit here. What kind of sprinkler spacing do you have? What kind of height do you have those sprinklers installed at? What kind of drop sizes are we going to get off those devices? What nozzle size do we need? What do we need to have for regulation of pressure? And really maybe the most important piece on this whole part is making sure that pressure in your pivot is in the proper range. If I could stress nothing else, I encourage you to go buy a good pressure gauge, put it out on the outside end of your machine, and the pressure you're measuring should be 5 psi above the regulation pressure of your regulator. If you do that, your system's going to be in pretty good shape, unless you have a lot of worn parts. So let's walk through some of this. When we look at a center pivot, we're looking about, where does the water go? How can we most efficiently get this water that we apply to stay in the root zone and be available for crop water use? These evaporation, the spray and the evaporation of droplets, many times I'll hear from people that those numbers are 20–30% of their application. Quite frankly, we cannot show that numbers anywhere near that amount. Maybe it's 5–6% on the upside. And so generally, this is also driven a great deal by the size of the individual droplet that the sprinkler is emitting. And so if we can choose the right devices, we can get larger diameter droplets, as we'll see in a little bit. Those larger droplets are not prone near as much to this evaporation and drift. So for most cases in Nebraska, we're going to recommend go with that little larger diameter droplet, and you really can minimize some of these drift and evaporation losses. Some of the water we apply stays on the canopy, as we show on the left-hand side. Now that water evaporates very quickly off the canopy compared to the rate of transpiration through the plant itself. What we have found in our research, though, is as soon as we wet this canopy, the transpiration rate basically drops to almost zero. And so there's a period of time while this water that's retained on the canopy is evaporating, the transpiration is reduced. And so the evaporation off the canopy is not a complete loss. It's kind of a net between what transpiration would have been and what the evaporation actually was. Evaporation from the soil, it's pretty hard to avoid that unless we go to a purely LIPA system. We've not been able to make those work very well in Nebraska for our soils and our terrain. So you're always going to have a little evaporation. We can suppress that evaporation some by more residue in the field. Hopefully we're doing a good job of scheduling irrigation, so hopefully we're not seeing this deep percolation being an issue here with our pivots. So a lot of what we're most concerned with is going to be this runoff number. We want to be able to select sprinkler packages that will minimize how much water is running off from where it's applied, either going to a low area in the field and leaching water and nitrogen out the bottom of the root zone, or actually completely leaving the field and being used by weeds somewhere offsite. So we're going to spend a fair amount of time thinking about this runoff issue. An important characteristic we have for a sprinkler system is that what we call the wetted diameter. So if I were to choose a low angle impact sprinkler like I'm showing up here, if I put that up on top of the sprinkler pipe, it might throw water 45 feet on either side of the pipeline. So I'm getting a distance along here of the wetted, what we call the wetted diameter. So generally the impact sprinkler is going to give us the furthest distance, going to throw the water the furthest distance. If I were to put maybe a rotator, a product made by Nelson Irrigation Company, I might put one of those up on top of the system today. There's some new devices out that work real well up on top of the system. It doesn't throw water quite as far as the impact sprinkler, so maybe I only have about 72 feet of distance that's water on each side of the pipeline. We're still putting out the same depth of water, so if I was trying to put an inch of water on with the impact sprinkler, and I also want to put an inch on with the rotator on top, still going to put on the same inch, but I'm going to put it on a little faster with the rotator. I'm going to have a little higher application rate, but not going to apply it quite as long. Now we have a lot of different choices today. You might look at a rotator that we would put then on a drop tube underneath the pivot. That's going to reduce that distance of throw, maybe another 12 feet or so, kind of depends on how high we install it. Certainly it's not just Nelson products, it could be a Seninger product like the iWob or variations of their wobbler. As I go even further, maybe I put a spinner out there, or I might put in some smaller devices from Seninger. We might see a decrease in that wetted distance, the wetted diameter that we water. If we were to put sprays or something up on top of the machine, we might get even less. And finally, if we put some spray heads on drops, put it down just the top of the canopy, I might only be throwing water about 24 feet. Now, we still put the same amount of water on with this system as we did back up here with this blue one. So if I'm throwing it about 1/3 the distance, then my peak rates have to go up by about 3 times. So we're applying water much more rapidly with the system here than we are with the system back up here. And so we have to think about how fast we're applying it compared to how fast the soil can absorb that water. It also makes a difference in where we locate those devices within, either above or within the canopy. So this is showing a situation where we might take a spinner. If it were 6 feet above the soil surface here, then what we would see is it's going to give a radius of throw of about 54 feet. If we dropped it down so it was only 3 feet above the ground surface, we might reduce that wetted diameter by about 6 feet. And so the height of that device has an impact on this wetted diameter. And eventually that's going to have an impact on how fast we're applying water and what potential runoff we might have. We did some work out at Alliance where we actually put these devices down in the canopy. So we had some spinner devices that were 42 inches above the soil, really about ear leaf height in the field. And what we did is we went out and measured the soil water the night before, and then we irrigated that evening, and then the next morning we went out and measured the soil water. So what this diagram is showing here is this yellow line is representing the change in soil water from the night before we irrigated till the next morning after we had irrigated. So where it happens to be higher, like here, this is showing that there was an increase in soil water at the location. If I go a little further over, maybe over there at row number 10, we really didn't get any water in the soil at all at that location. There's very little change in that amount of storage. And so what has happened is we have put these devices out. The spacing in this particular field was 12.5 feet. But what we've done is we put those in the canopy. The canopy has knocked that water flow down, and so we're not getting the spread of water that we want between those locations. And so maybe in 2002 or 2012, 2 very dry years, people had not noticed any uniformity problems, but in those very dry years, they go out and they start to see rings in the field. And that's probably because we've dropped these devices down in the canopy too far, and we've knocked down that pattern, and we're not getting the uniformity we want between those devices. So my recommendation is to leave these things up here. Let's get back up here at the top of the canopy, just below the truss rod height, or go up on top of the pipeline system so we get a good throw. We're not saving as much water by dropping these down the canopy as we think we are. An important characteristic that we have to think about is the amount of water that we can store in the soil before it begins to run off. So if we look up here at the top, what we see is there's some natural depressions in that soil system. And so these little blue areas represent small little reservoirs in here that we can fill up that will store water without water running around in the field. After we've exceeded the amount of water that those little reservoirs will store, then the water starts to flow across the field and we start to get these runoff problems. Now, if the field has some slope, even though these little reservoirs are the same size here as up here, what we find is that we can't store as much water in these reservoirs because they're on a slope. Water kind of runs to one end of that little basin. So as we increase the slope, we get less storage. And so up here, if I'm very flat and I have some storage, I can probably put on a little more water, or I can put on water at a little higher rate and not have a runoff problem. Down here, my problem is I don't have as much water that I can store in the surface, so I have to be a little more careful in this setting here. We also have to worry about the operating pressure of our system. And so this would be an example of maybe the correct operating pressure. What we find is that when we're at the right pressure, at the pressure that in range that these devices were designed to operate in, we get a nice breakup of the water droplets. So what we would see typically is we'll see the small water droplets that are in the middle, and we'll see the bigger water droplets go to the outside. And that's simply because the momentum in a large drop is so much that it overcomes resistance to flow through the air. And so the big droplets have a lot of mass and a lot of momentum, and they go a long ways. The small drops are much more affected by the relative velocity of the drop to the air. And so they decelerate very quickly, and those small droplets end up falling very close to the pivot point. And so this is a pattern that we would expect to see that develops here if we have the right pressure. Now, if we don't have enough pressure and the pressure is really low, we don't get a very good breakup of that jet from the sprinkler. And so what we get then is a lot of large diameter drops, but also because the pressure is low, they don't have quite the same velocity as they had with the correct pressure. So we get a lot of big drops that don't go quite as far as they did before. And we end up getting what we call a donut pattern. We kind of get a big donut shape where a lot of the water is kind of applied in that donut. There's a dry area in the middle of the whole of the donut, and we don't throw it quite as far as we did before. So we don't want to be here. We want to make sure we're in the right pressure range for our system. On the other hand, if I run the pressure up too high, what happens is we get too much breakup. And so we get a lot of the water jet is breaking up into many small drops, almost atomized or almost a mist. What happens here now, we have lots of small drops, they don't travel very far, and so we get water kind of accumulating right around our sprinkler. And if we have a wind situation, now these drops are free to blow around. So we really need to make sure we're maintaining that device that we're using to apply water in the proper pressure rating that it was designed for, which you can get from any of the manufacturers for your system. There's a wide range that you can operate over, but you need to make sure you're in that correct range. The other situation we run into is what happens when we put sprinklers on some of the rolling terrain we have here in the Great Plains. What we know is that if we look down here, what we know is that a 23-foot elevation change in the field represents a change in water pressure of 10 pounds per square inch. And so if we have a device that was designed for, say, 20 psi, when it goes up on that hilltop, it may not have enough pressure in order to maintain the flow. So what we see in this top diagram is that we may be underwater at that hilltop because we didn't have enough pressure. We may overwater down here in the valley if we don't have a regulator, because now we have more pressure than we want. If we use a pressure regulator, we certainly can even out the flow rates here in the valley, and maybe even up on the hilltop we might even do a better job because more water is in my pipeline to be able to apply to the top. So in a lot of cases we need to think about using regulators in some of our rolling fields here in Nebraska. Now, what is a pressure regulator? Well, we're showing on the left-hand side here of a regulator. Obviously water is flowing top down in this case. So the pressure at the inlet is one value, and the pressure below the regulator is the other. We call that the outlet pressure. So what we're diagramming here, this is actually a figure from Senator Irrigation, but what we're showing here is the inlet pressures on the x-axis and the outlet pressures on the vertical axis. And so in this particular case, as we look at this, suppose we have a 10 psi regulator. This is showing that the pressure, we're kind of following that pink line as we go up until we get to about 10 psi. After we get off to the right and we get above that, then the pressure tends to level out and we stay at 10 psi on the outlet pressure. So the whole idea of a pressure regulator is it will maintain a constant outflow or outlet pressure for varying inflow pressures once you get above a trigger level. Now, the other thing you'll notice on this device is that there's about a 5 psi loss of pressure through the regulator itself. And so if we're running here, if we designed our sprinkler package, in this case, to have that wobbler device operating at, say, 10 psi, I would want to have 15 psi available above the regulator so that I take account of how much pressure loss we're going to have due to friction within the regulator itself. So know what your regulator pressure is and just make sure the pressure in your pipeline is at least 5 psi above that point. You really ought to go out in the highest spot in the field, the furthest away from your pivot point, to make that measurement. We see 7 to 10, 12 psi friction loss in the pipeline itself on most pivots. So you really need to go at the outside in and get up on that hilltop because there's about 10 psi change for 23 feet of elevation change. If you get it far in, up on the hill, and if your pressure is above 5 PS above your regulator, then you're doing a pretty good job. If it's a little more than that, it's fine. If it's quite a little less than that, then we've got a problem between the pump and the well, most likely. So this is what a regulator does. The other important characteristics we have from sprinklers is the size of the nozzle. And so what we see, this is a chart, this happens to be from Nelson Irrigation Company. And what they do is they label their charts here. This is the example we're showing on the left is a size 26. So we have a white colored nozzle, has the number 26 stamped right on it. If we look over here, what we see is that this is that column for the white 26. And so what it's showing is for pressures from 6 to 50 psi, we're showing how many gallons per minute is flowing out of that device. What we know is when you double the pressure, you're going to increase the output through that nozzle by about 40%. If you double the size of the nozzle, so if we go from a 26 here to a 13, we would get 4 times the flow of water out of the device by doubling the size of the nozzle. Now what this 26 means is we're getting about, what Nelson does is they size their nozzles by 128ths of an inch. So a 26 nozzle is 26 over 128ths of an inch. So the other thing they've done is they've color coded these nozzles. So now then you can look at the color and know, if you have this chart, you can look at the color and know what size nozzle is without having to climb up there and look to see what the number happens to be in the nozzle. Well, what happens if we don't have the right pressure? This is looking at a pivot with 30 psi regulators designed for about 750 gallons a minute. And so what we're looking at is distance from the pivot point, and we're looking at the depth of water that's applied. So what we'd be looking for is a system like in the green. So if you look back here, up here at the top, you see this green in this area. So that green is really what would happen if you had all the pressure that you needed. For this particular device, our design pressure at the pivot point was 49.5 psi. And so the black line that we see here, not a lot of difference. What happens if our pressure at the pivot point drops too low? So suppose the pressure in our pipeline dropped to 31.7 psi. What the white line is showing out here then is the distribution of water along the pivot when we didn't have enough pressure at the pivot point. And what we see is not a lot's happening on the inside part. There's a lot of things that are happening out here on this outside part. And so we tend to underwater the outside part of our pivot. And with a normal 7-span machine, about 25% of your land area is under that outside span. So when we don't have enough pressure in a pivot, we end up underwatering that outside span, and that causes us to have less water applied on about 25% of our field. So we really need to check that pressure and make sure we're keeping it in the right zone. So what information are we going to need? We're going to need to look at our characteristics of our field, our soil series and texture, our slope, and then we have to think about managing for residue and how we can look at the depth of water we apply. We really encourage you to go look at this product. This is a product developed by the USDA, the Natural Resources Conservation Service, and this is a way to go out and get a soil map for your field. Now it's not perfect, but it's a really good way to hone in on your individual location. So what you do is you go to this web page, you click on that little Start WSS there button in the middle, and eventually you'll come up with a diagram that looks like this. We have told it where we want it to be. You can do that by township, section, and range, or you can do it by county and state, whichever way you best find your field. What we've done here is zeroed into a pivot. Once we've kind of gotten the map to the right scale, then we need to outline our field here in what's called the area of interest. So you click that little button there that's in the circle, in the blue circle. That brings up a little blue rectangle. We stretch that rectangle over our field, and then we simply click on the soil map. So now that's told it what land area we want to look at in the background picture. Once we've done that, then we can click on soil map, and this will tell us then the soils in our field. And so what you can see here is the predominant soil in this field is a Hastings silt loam. That's this 3864 soil. We've got a little bit of, and that happens to be, this one happens to be at a 0 to 1% slope. We have a little bit that is 1 to 3% slope. That's this 6.6 down here. The 3887 is a silty clay loam. and it's that 3887, so it's the one that's right up here. So you get a map of the soil types in your field. Now this is what you would have gotten if you would have went to your old paper copy and just looked at it for your field. Very handy to do this on the internet, pretty easy to do. So from this we get our soil types, and we even get some slope that we can use. And so we have some guides. If you look at some of our programs, go out to the water website, you'll find some tools you can use to maybe help you identify and select some sprinkler nozzles that will avoid runoff for you. Another thing we want you to really think about is maintenance. And in the springtime, we like to have you go out and just see what is going on with this pivot. This happens to be a case where in this top pivot up here, you'll see we're missing a nozzle right next to the tower there, seems to be plugged. There's an example down at the bottom where we got a big leak near that outside tower. In this case, this is probably 3 to 5% of your field area that's been affected by that leak. And so, you know, if you get out there when you don't have a lot of crop growing, you can see these problems very easily, and you know, it doesn't take much to fix some of these things. You know, if it's a leaky gasket here, it's a little more involved, but not so bad. Certainly getting rid of plugged systems or leaking nozzles. You can also watch the devices and see if they're operating like they should. Sometimes we recommend that you go out on that outside span. Maybe you buy a new regulator and get a new device that matches your other one. Put it in there, put in the right size nozzle that you had before, and just compare how the system operates with the new equipment compared to the old one. You only need to do a couple of drops on a span. If your old system's operating, rotating at about the same speed as the new one, you're probably okay. You know, if the old ones are going around a lot faster than the new one, well, maybe it's time to think about, maybe I should go ahead and make that upgrade to that sprinkler package. So some summary here, what we really want you to do is think about selecting the right kinds of nozzles for your field, right kind of devices. We can do that by looking at the soil survey, and we have to maintain that system in order to be able to achieve the potential high efficiency that we get with center pivots. They really have the ability to do well, but we have to manage to achieve that level. Again, this is a cooperative effort amongst various agencies and the university, and we're thinking about how we can improve irrigation management to minimize depercolation and protect water quality. Thank you.